Hi everyone, so today's topic is inferences for regression. These are the key points from the last lecture. So we learned about goodness of fit test and chi-square distribution and multiple different types of chi-square tests. Let's start with this example, predicting percent body fat. So measuring body fat is tedious and expensive. So if we can predict percent body fat from easily measurable variables like height, weight, or waist size, that would be really nice. So let's see this example data. So here x-axis is the waist size and y-axis is percent body fat. And as you can see, they have really a linear relationship. So let's say we build this equation from the linear regression we learned. So percent body fat, the estimated value for that equals minus 42.7 plus 1.7 waist. So if we increase 1 inch for the waist size, and there will be 1.7% body fat increase. So this is basically y hat equals beta naught plus beta 1x. So this is the intercept. The question we want to address is how useful is this model? What can this model tell us beyond the 250 men data in this study? So generalizability basically. And this is the histogram of percent body fat that from our data, from this data. And as you can see, more people near the mean of percent body fat. And the idealized regression line should be for each x, the distribution of the data around the regression line shaped like this, the normal distribution. And we want to quantify the amount of the variance around the regression line, and using that, we want to quantify how well our model explain our data. So this residual is epsilon here. So for doing this, there are assumptions and conditions. All these are similar to the assumptions and conditions we learned for the linear regression. So linearity assumption, equal variance assumption, and we talked about the plot thicken condition, that is the residual plot, and normal population assumption. We can use the normal probability plot, and also independence assumption. So errors should be independent of each other. So this typo, and examine for that we have to examine residuals for evidence for any patterns, trends, or clumping or band. And if the data are related to time, if that is time series data, we have to plot residuals against time as well. So what is the order of examining the assumptions and conditions? So first of all, we have to make the scatter plot of the data to check the straight enough condition. So this is really basic step. So if the relationship is curved like that, like this shape, we can re-express the data or stop. Or we can use other types of model like quadratic model and so on. And if data are straight enough, we can fit a regression and find the residuals, epsilon or e, and predicted values, y hat. And make a scatter plot of the residuals against x or predicted value, y hat. This plot is called residual plot, right? And this plot should have no pattern. And we have to check for any band and so on, or any thickening, and for any outliers. We learned about this, so I'm gonna skip. If the data are measured over time, we have to plot the residuals against the time to check for evidence for any patterns that might suggest that they are not independent. There could be a pattern dependent on time. So we have to check that. If we scatter plot look okay, then make a histogram and normal probability plot to check the nearly normal condition. If all conditions seem to be reasonably satisfied, we can go ahead and do inference. So before digging into the regression inference, we can talk about intuition first, because the actual calculation is quite complicated. Just knowing the intuition is really important. So what can affect how much the slope vary from sample to sample? That is basically the stability of beta, and more stable beta would be better, right? The first one is spread around the line. If the data has really large spread and smaller spread like this, what would be more stable? Like for example, if let's say we are sampling part of this data, population data, and I would say this is much more stable because removing some of the data will not change the line much. But here, if we remove some of the data like this, and then line will be changed. This is gonna give us better stability of beta. What is the metric that quantify this. This is residual standard deviation. So the spread from the predicted y. So y minus y hat square and sum of that and divided that by n minus 2 and square root. This is the residual standard deviation. And also, interestingly, spread of the x is really important. What would you say? Which one is more stable? I would say this is much more stable, because if we remove some of the dots, it is going to be, the line will be similar, but the small removal of dots here will change the line dramatically. So if we have more broad range of x, the line will be more stable. So this is going to improve the stability of beta. And sample size is also important. So small sample size, the line will be really affected by small number of dots. And if we have more data, the line will be better estimated. So this is going to improve our stability of beta. The standard error for the slope has these three components. One is spread around the line that we just talked about, residual standard deviation, and spread of the x, that is standard deviation of x, and sample size n. The standard error for the regression slope is this. Given that smaller spread around the line will be better, will reduce the standard error of the beta, so it's in the numerator, and larger sample size will reduce the standard error, so it's in the denominator. Also, spread of x will help to reduce the standard error of the beta, so it's also in the denominator. Here, as we talked, the residual standard deviation can be calculated with this equation, and standard deviation of x is this, right? We know this. It's very similar, but a little bit different. This has y hat here, x bar. So here we can say this standard deviation is the residual standard deviation with a mean as a model, a simplest model, and this we have a regression model and the residual based on this model. After that, the inference about beta is similar to inferences about means. So beta we observed, and we have the null hypothesis beta 1. It's usually 0. This is null hypothesis, and divided that by standard error of the beta. This follows t-distribution with the degree of freedom of n minus 2. Because we have two parameters, slope and intercept, the degree of freedom becomes n minus 2. It's the same for intercept, so we have beta naught minus the null hypothesis beta naught, and that divided by standard error of the beta naught. That follows t-distribution. But we are not that interested in this. We are more interested in this. Usual null hypothesis is slope equals 0. So this, therefore, t n minus 2, the degree of freedom, it becomes simple like this. And 95% confidence interval for beta is the same. Like if we note the standard error of the beta 1, but just note that the degree of freedom is n minus 2, not n minus 1. So for means, we had a n minus 1. And more than the slope, we want to know the standard errors for predicted value. So for example, we want to know that the mean percent body fat for all men with a waist size of 38 inches. So what's uncertainty of the estimated mean body fat percentage for the waist size of 38 inches? And also, do we want to estimate the percent body fat for a particular man with a waist size of 38 inches? More often, we are interested in this than this, but we can talk about this. So the first one is y hat nu. So this is the estimated value for specific x value. So this is the conventional equation, estimate plus minus margin of error. And margin of error is the critical value times standard error. But here, we have different standard errors for different questions. So for the mean, so the first question, standard error becomes like this. And here we have a standard error of the beta 1, but we are less certain of the slope, or we are going to be less certain of our prediction. And given that, usually we have more data in the middle, in this mean area, and our estimation will be more precise for near the mean. So farther, the prediction for x nu from x bar, we are going to have the lower certainty. So we are multiply this with the x nu minus x bar. So this is specific value, how far that is from the mean. If there is more spread around the line, we have lower certainty, like really narrow dots compared to really broad spread. Of course, the more spread means lower certainty. Therefore, we are adding this component. And if we have more data, we have higher certainty. So we divided that by n. And for individual data point, you have one more component, that is the variation of individuals around the predicted mean. So this is residual standard deviation, how spread the dots around the line. And by adding this, we are having more error component to that. So standard error of each point is a particular man, we have this additional component. But usually we are more interested in this, and if you see some regression plot, you will see this line more than this. In the papers, we use this green line more often. Okay, so this is it for today's lecture, and don't forget to solve the quiz, and see you in the class. Bye.